Our next presentation is by Mehraud and Connor, and they are going to tell us about the various substitution effects on anticrine analogs in their anti-cancer drugs that they've been researching. So let's welcome Mehraud and Connor.
All right, so I'm Mehraud. I'm Connor, and what we are doing, as Sean so graciously told us, is we are testing the various substituent effects on the 4 series of Para-disubstituted-O-benzylhydroxylamine as an anti-tumor agent. So first we want to talk a little about cancer. It's a disease that's becoming more and more known as time goes on, and in the United States it's the second biggest killer behind heart disease. Cancer occurs when normal cells, they're exposed to some form of mutation, usually from radiation, and what causes for the cell to rapidly divide and to undergo mitosis very quickly, and therefore the cells form a big clot, and that is what's known as a tumor, and then that can inhibit function of central organs, and then if cancer is left untreated, what happens is that it will metastasize, and that means that it goes out throughout your body, and then it can affect the other organs, and then it can cause major problems for oneself.
And that's where treatment comes in. So meta-anticrine or anticrine meta and ortho was a treatment option prevalent in the 70s for both leukemia and Hodgkin's disease, and basically its effectiveness lay in its ability to intercalate between the 2 nucleotide base pairs, and you can see that on our animation. And basically what that did was it prevented the DNA replication because it kind of just sealed it together.
And so, as he briefly mentioned, intercalation, basically what happens is that something, in this case it's the acridine at the bottom of the molecule, it will go in between the base pairs of DNA, and then it will just hold it there, and that's what stops the DNA from, it affects its replication and its growth process. And what the drugs meta-anticrine and ortho-anticrine do is that not only do they act as an intercalator, but the section on top, that is a hydroxylamine. What that does, it acts as a poison for the replication enzyme topoisomerase 2. Topoisomerase type 2, its job in DNA replication is to split the DNA and then reanneal it in order for the cell to undergo mitosis. But when the drug binds to the topoisomerase, it stops it from reannealing, and so the DNA is left cut in several locations, and therefore it causes the cell to go through cellular apoptosis or cellular suicide.
Okay, and just to clarify, the difference between meta-anticrine and ortho-anticrine are the O bonds, or the oxygen bond to the carbon on the benzene ring, kind of. And yeah,
they're on different points, and that's where the meta and ortho come in. And these drugs are really, as you said, they were prevalent in the 70s, but there's one issue with it, is that these drugs, they were unstable, mainly because of something that we call, or that is known as nucleophilic attack. So if you see on the nitrogen here, this is what we call an excellent leading group, and what happens is that as the drug is put into the body, a nucleophile, which is just something that can switch into the molecule, will try to knock off this bond right here with the carbon on the phenyl group. And what happens is because the nitrogen, it didn't have a good amount of electronegativity surrounding it, what happens is that the acridine would break off from the molecule, and it would do damage to other organs or to other areas in the body as in healthy cells. And so this was bad for 2 reasons. One, because it shortened the half-life of the drug, meaning that most of it would be destroyed, but also that it would have to be put into large quantities to counteract that, and therefore it would cause damage to the body as well.
So this is a specific molecule that we're synthesizing, and it's O-benzyl N 9'-acridonyl hydroxylamine. And basically what we substituted was the R3 group, which is the para group. And what I did was I put a nitro on that R3, and he put a chloro. And basically we tested those results, or that.
And so what you'll notice about this drug is that what makes it different from meta-anticrine and ortho-anticrine is that right here on the arm of the molecule there's an oxygen. And the reason that the oxygen is there is because it's really electronegative. It's very electronegative, and so therefore it prevents the nitrogen from breaking off, which overall raises the stability of the molecule and allows the treatment to be done with less quantities, and therefore the acridine is less damaging to the human body.
So this is kind of a quick run through of our methodology. We had to, of course, synthesize the drug. Now, we didn't completely synthesize it, so we got through step 4 and we finished that step, but we were not able to do step 5 and get our final molecule and purify it. So we'll kind of go into that.
Yeah. And so just breaking down the methodology. So in order to start with it, the first main step we did was the construction of the oxyphthalamide. For me, it was the 4-chloro. For Connor, it was the 4-nitro. And he can talk about what we did to make that.
Okay, so basically we conducted a reflux, which is basically you take a round bottom, you put a condenser on that, and you run cold water through the condenser so it precipitates the solution as it evaporates. And you place that on a nest which heats the round bottom, and you conduct it while it's kind of spinning so the reaction can occur. And we conducted it with baking soda in our specific compounds that we substituted, and then the tetrabutyl ammonium hydrogen sulfate, which is that weird one right there, then deionized water, dichloromethane, and hydroxyphthalamide. And that's what produced our phthalamide, and that was just one step in our multi-step synthesis.
So then after the reflux, we were able to take the take the product and put it in for extraction and washing. Basically what this does is that it separates the product from other things, and it also helps purify it. As you can see right here, this is a separatory funnel. The layer on top, that is the aqueous layer, and the layer on bottom is the organic layer. And our product, the oxyphthalamide, was embedded in the organic layer. So basically, in order to extract that, we used dichloromethane, which is what we use to just pull the layers apart, and so we could extract the product. And then once it underwent extraction, we were able to wash it using acids and bases in order to just get everything icky out.
So, of course, after extraction and the washing process, we had to evaporate the solution, and basically that was dichloromethane, so it had a low boiling point. So all we had to do was do some cool things with this machinery. We basically lowered the pressure, which helped it boil faster, and we increased the temperature, and that evaporated it really quickly and left our product.
So after we had the product, what we did to make sure that we had confirmed the product is what's known as an NMR, or nuclear magnetic resonance image. And so basically what this does is that it helps us really know what exactly is in our product. The version of the NMR we did, it was an H NMR as in a proton NMR. So as you can see right here, this is a drawing of the molecule that this was for my molecule that I hope to get. And so this is what we can analyze the NMR. So if you look at this huge spike right here, that is the CH2 group that would be right there. And then these two groups over here, they're amplified up here. This NMR was a bit strange, but using some work, we were able to deduce what these were. Right here, this is the hydrogens on the phthalamide group. This is what we call a doublet of doublets, and so that helps us confirm that we knew that the phthalamide was there. And then these spikes right here, these were on the phenyl group. These were the hydrogens there and there on the phenyl group, so we knew exactly where we were getting with that. And then right here, this is the dichloromethane, which was just left over from the process. And we have water right here as a contaminant, but basically we knew that we had this product confirmed.
And as you can see, the NMR for my product was very similar since this is a proton NMR. The difference is, though, that the peaks did shift to the left a little bit. And the main...
And on Connor's, he was able to produce the salt, and this is an NMR of that. Basically, just as NMR confirms that the product. Unfortunately, the reason we only have one NMR for that is that the chloro salt did not form. Mainly when we put it through the acidic reflux and into the hydrochloric gas bubbling, we were unable to induce a precipitate to form, meaning that the salt would not form. We went back and we tried extraction and washing again and rotovapping again, but we made sure that solution was alkaline before we did acid bubbling, but there was we couldn't figure out why. We assumed that it's because maybe we got water into the reaction sometime earlier, but that is what
And real quick, these peaks right here, you can use those to confirm the molecule, like Mehraud said. The low peak is the hydrogens around nitrogen, so that confirms that part of the molecule. These two peaks, kind of between the 9, 8, and 7, that's basically the benzene part, so those are those hydrogens on the benzene. And then the final peak is just the CH2 that bonds the two parts of the molecule.
And so after we did the salt testing, once he got the salt, we were running a bit short on time, so what we used was our mentor had graciously prepared purified samples at 99% of the drugs that we were testing. And so based on that, we were allowed to use those drugs to complete the actual testing and to see how well it intercalates with DNA and could act as a cancer drug.
And basically what we did was we determined the absorbance using UV vis, and from that we calculated the molar concentration within the solution, and it calculated that molar concentration needed to be multiplied by 2, so when you added it together, the molar concentrations would be equal, and establish that 1-to-1 ratio that would allow us to get exact viscosity results.
Yeah, and the way that we did that, as you mentioned, the UV vis, that stands for ultraviolet visible spectrophotometer. And what we did is that our mentor prepared a solution of Cap-finest DNA, and so therefore we could use that to test to see how well it intercalates. Then after we put that through there, we inserted our known values into Beer's law, and that allowed us to help find the concentration of the drug that we needed.
So the results for viscosity, of course, the DNA control on the O-benzyl 9' acrodenylhydroxylamine, those two results were very non-viscous, so not very viscous at all. That's repetitive. But then these two were obviously remarkably more viscous, and basically that indicates that it binds well with the DNA. And the reasoning behind that is when an intercalator binds with DNA, it straightens out the strands and lengthens them, so that makes the solution more dense in a way, and they can't interact with each other to a point where it's more viscous.
And as you can see, these two right here, they're just controls. The DNA control, as we mentioned when we were testing viscosity, this is a viscometer. Basically, it's just used with timing to test, and you can calculate your viscosity. So with the just DNA alone without any drug, it was 0.005 millimeters squared per second. And then with the drug that we were producing, but without the substituent group changed with just hydrogens on the phenyl group, it went up by 0.0001, so it's ideal. And then with our own drugs, as you can see, the chloro and the nitro were significantly better at intercalating with the DNA, increasing their viscosity.
So these are more results. These are basically QSARs, which it stands for Quality Structure Activity Relationship, and basically what it does is it relates predictor variables and response variables. And the predictor variables in this case are the Hammett sigma values, and the response variables are the kinematic viscosity and the thermal denaturation values. And basically what this did was it shows us that there's a correlation between the two, and the same trend can be seen in both graphs. It's kind of hard to see, but the range is different. But from 0 onward on both graphs, you see a similar upward trend. And basically that confirms that our molecules that we synthesized basically acted as we would expect them to.
And if we can go into this a bit more, the Hammett sigma value is just a constant that tests it's a constant for the relationship between two substituent groups with any first one and a second, and it's a constant that tests for that. With different substituents, like right here, this is the nitro. Yes, so this is the nitro on the Hammett sigma, and this is the chloro. As you can see, the nitro is a tiny bit higher, but the chloro is also very nearby, showing that they were both excellent intercalators, even though the nitro was slightly better. And then if you look over here with the thermal denaturation, the one that's on the 0 line, that's just the plain hydrogens. Right here is a methyl group on each of them. And so if you look at that, you know that hydrogen was pretty much the worst intercalator as substituent groups for the phenyl group. And on top of the methyl is better. And then right here, this is a bromo and a chloro. The reason that we can't put a nitro up there is because when we attempt to take thermal denaturation of nitro, a precipitate out of solution, and so that rendered the thermal denaturation improbable.
Okay, so these are our thermal denaturation values, and this is Mehraud specific results. And basically you can see from the normal DNA that the curve steepens, and that basically indicates that the melting temperature increases, which is what we want because that indicates that it's intercalating very effectively.
Yeah, and as we mentioned before, like as you can see this one, it's a different graph, meaning that it's intercalating stronger. And the reason that we couldn't test Connors is because it precipitates out of solution, and so it can't be used in.
So discussion, the O4-chlorobenzyl in 9'-acrobenylhydroxylamine. It had a very large viscosity, but its higher temperature for thermal denaturation also indicated that it is a good intercalating agent, so both of those pieces of data coordinated. The O4-nitrobenzyl in 9'-acrobenylhydroxylamine had a large viscosity, but thermal denaturation could not be determined. And because of that, basically we know that it would not be conducive in a human body because humans are aqueous, and you don't want something that precipitates in your blood. That would be really bad. So, yeah.
And yeah, it's really exciting for us is because even though they are both excellent intercalators, and the nitro unfortunately would not work in aqueous-based life forms as humans, the 4-chlorobenzyl, it shows that it is, in relationship to the anthraquins that we showed earlier in the 70s, it is a stronger intercalator, and because it has a shorter half-life, a longer half-life, it's not as toxic, and we don't need to put as much quantity into the body, and so we can, this is something that's possible to use in future treatments.
So that's basically our conclusion. We know even though the nitro substituent was the most viscous, the chloro substituent was the most viable cancer treatment option, and we know that because of the thermal denaturation values as well as the viscosity values, all of which indicated that it is a great intercalator in addition to the fact that it doesn't undergo nucleophilic attack. So it thusly has a longer half-life.
So these are lovely references. And we'd like to give a very special thanks to our mentor, Ms. Alyssa Carlson. We could not have done it without her.
Also, we would like to thank Sean Hoskins for going over our slides and presentations and work and just telling us what to do.
We'd also like to thank Dr. Michael Mosher, who's the head of the department. We'd like to thank him for letting us use his lab and his fancy stuff.
We would also like to thank Sean Johnson, because while we were in the lab, he also helped us out a lot too. Both Alyssa and him were really good to us.
And then we'd also like to thank Ms. Lori Ball as the program coordinator for FSI, as well as the University of Northern Colorado for letting us work on campus and stay here. And also I'd like to thank XL Energy for supporting not only my room and board, but also my research.
And I would like to thank Wells Ranch and Union Pacific for supporting my room and board, as well as my research here as well.
Thank you.
Value to us, and you said that the